Hello and welcome to Majhi Academy. Once again, let us read the question. Following graph shows the loss characteristic of a sheet of ferromagnetic material against varying frequency f. Pi is the total iron loss at frequency f. Hysteresis and eddy current losses of the sheet at 100 Hz frequency are option A 10 watt, 50 watt, option B 10 watt, 100 watt, option C 1 watt, 5 watt, option D 1 watt, 10 watt. Since figure shows the variation of iron losses with respect to frequency. Now remember the iron loss equation. Pi is equal to pH plus Pe, where pH indicates hysteresis loss, whereas Pe indicates eddy current loss. Now we know that hysteresis loss is directly proportional to frequency and eddy current loss is directly proportional to square of frequency. Now let us write iron loss equation in terms of hysteresis loss and eddy current loss and constant of proportionality. We get equation like this. Eddy current loss is equal to AF plus BF square, where AF represents hysteresis loss and BF square represents eddy current loss. Now let us divide this equation by F from both the sides. We get equation like this. PI by F is equal to A plus BF. This is the equation of straight line, where A represents intercepts and B represents the slope. Now let us compare this equation with the graph. Now you can see intercept A is equal to 0.01 and the slope B is equal to 0.001. Now we require to calculate hysteresis and eddy current losses at 100 Hz frequency. Therefore, hysteresis loss pH is equal to A times F means 0.01 multiplied by 100 gives 1 watt. Similarly, eddy current loss Pe is equal to B times square of frequency, which is equal to 0.001 multiplied by square of 100, which gives us 10 watt. Therefore, the correct answer is option D. Hysteresis and eddy current losses of the sheet at 100 Hz frequency are 1 watt and 10 watt. Second question. A 2 kV transformer has iron loss of 150 watt and full load copper loss of 250 watt. The maximum efficiency of the transformer will occur when the total loss is option A 300 watt, option B 275 watt, option C 500 watt, and option D 400 watt. Now question gives iron loss is equal to 150 watt and copper loss is equal to 250 watt. We know that maximum efficiency will occur when copper losses are equal to iron losses. So at maximum efficiency, copper loss must become equal to 150 watts. Now calculate total loss. Total loss is equal to iron loss plus copper loss, which is further equal to iron loss 150 watt, and due to maximum efficiency, copper loss is also equal to 150 watt. Therefore, total loss becomes 300 watts. Therefore, the correct answer is option A. The maximum efficiency of the transformer will occur when the total loss is 300 watt. Now, remember the key points. Iron loss remains constant. On the other hand, copper loss varies as the square of load current. Similarly, maximum efficiency occurs when copper loss equals iron loss. Third question, potential transformers are used. Option A as protective device in high voltage circuits. Option B to measure high AC voltage. Option C to measure high DC voltage, and option D both A and B. Now first understand what a potential transformer or PT actually does. A potential transformer is an instrument transformer used to reduce very high AC voltage to a lower, safer value so that measuring instruments like voltmeters can measure it safely. So the main purpose of a PT is measuring high AC voltage. That means option B is correct. Now let us check other options. Option A says protected device. Since a PT is mainly used for measurement, not directly as a protection device, so this is incorrect. Now option C says measuring high DC voltage. We know that transformer works only with AC, not DC. Therefore, this is definitely wrong. Since option A is wrong, option D also becomes wrong. Therefore, the correct answer is option B. Potential transformers are used to measure high AC voltage. Now remember the key points. Transformer works only with AC, and potential transformer is nothing but an instrument transformer used to reduce very high AC voltage to a lower value or safer value so that voltmeters can read it easily. Therefore, option B is the correct answer. Fourth question, a 20 kVA 2000 volt by 200 volt two winding transformer when used as an auto transformer with constant voltage supply of 2000 volt is capable of handling option A 320 kVA, option B 220 kVA, option C 20 kVA, and option D none of these. Now let us assume it is a step-up auto transformer. Now you can see the circuit diagram on the screen where 2000 volt is the primary input voltage and 2200 is the output secondary voltage. Now in this case 2000 volt winding and 200 volt winding are connected in additive polarity. Now we know that when we convert two winding transformer into an auto transformer, the voltage across the winding and current through it remains unchanged so that temperature rise remains constant. Now calculate current rating of each winding. High voltage winding current, which is equal to 20,000, that is 20 kVA divided by 2000 volt, gives us 10 ampere. Similarly, low voltage winding current 20 kVA divided by 200 gives 100 ampere. Therefore, total current driven by the transformer from the primary side is 110 ampere. Since 200 volt winding is connected in series with the load directly, therefore whatever current flows through the 200 volt winding, same current flows through the load. Now we know that kV rating of the transformer is the product of voltage and current. Now for simplicity, let us consider output side. Output voltage is 2200 and output current I2 is 100. Their product gives 220 kVA. Therefore, option B is the correct. Rather than doing such heavy calculation, the kV rating of the transformer can be calculated directly by using the formula, that is kV rating of auto transformer is equal to high voltage divided by high voltage minus low voltage, whole fraction is multiplied by rating of two winding transformer. High voltage divided by high voltage minus low voltage gives 11, that is 2200 divided by 2200 minus 2000 gives us 11, and kV rating of two winding transformer is 20, which is again equal to 220 kVA. In this way, we can calculate the kV rating of auto transformer when we convert two winding transformer into auto transformer. Fifth question. Power transformers are designed such that maximum efficiency occurs at option A 25% of full load, option B 75% of full load, option C 50% of full load, and option D near full load. The question asks, power transformers are designed such that their maximum efficiency occurs at what load? Now we know that power transformers are generally located at generating stations or substations and mainly used in transmission system. Moreover, power transformers operate at very close to full load for most of the time, or we can say near to full load, that is 90% to 100% of full load. So we design them in such a way that their maximum efficiency occurs near full load. Therefore, the correct answer is option D, near full load. Now let us talk about distribution transformers. Distribution transformers usually achieve maximum efficiency around 50% of their full load because their load fluctuates throughout the day. As far as given question is concerned, power transformers are designed such that their maximum efficiency occurs at near full load. So option D is the correct choice. Sixth question. In a single phase transformer, the copper loss at full load is 600 watts. At half of the full load, the copper loss will be option A 75 watts, option B 150 watts, option C 300 watts, and option D 600 watt. We have given full load copper loss is equal to 600 watt. Now we need to find copper loss at half load. Now remember an important formula. Copper loss varies as the square of load current. Now let us consider X is the fraction of load, then copper loss at that fraction of load is equal to square of the load fraction multiplied by copper loss at full load. Now VL of X in this case is 1 by 2. Therefore, copper loss at half load is equal to 1 by 2 whole square multiplied by 600, which is equal to 600 by 4 gives us 150 watt. Therefore, correct option is B. Copper loss at half load will be 150 watts. Seventh question. A three-phase transformer has its primary connected in delta and secondary in star. Secondary to primary turns ratio per phase is 6. For a primary voltage of 200 volt, the secondary voltage would be option A 278 volt, option B 1200 volt, option C 693 volt, and option D 58 volt. We have given data. Primary connection is in delta and secondary connection is in star. Turns ratio, which is the ratio of secondary turns to primary turns, is equal to 6 and primary voltage of 200 volt. We know that for delta connection, line voltage is equal to phase voltage, since phase voltage for primary side is 200 volt. Now we know that voltage is directly proportional to number of turns. Therefore, the ratio of secondary voltage to primary voltage is equal to ratio of secondary turns to primary turns. Now, on arranging this equation in terms of secondary voltage, we calculate secondary phase voltage as transformation ratio 6 multiplied by primary voltage 200, which is equal to 1200 volt. Now for star connection, line voltage is equal to root 3 times phase voltage. Therefore, VL is equal to root 3 times 1200, which gives us 278 volt. Therefore, the secondary voltage would be option A 278 volt. Eighth question. The iron loss in a 100 kVA transformer is 1 kilowatt and full load copper losses are 2 kilowatt. The maximum efficiency occurs at a load of option A 50 kVA, option B 100 kVA, option C 70.7 kVA, and option D 141.4 kVA. We have given rating of transformer is 100 kVA and iron loss is equal to 1 kilowatt and copper loss, that is full load copper loss, is equal to 2 kilowatt. Now we know that condition for maximum efficiency, copper loss is equal to iron loss. Now let us consider X is the fraction of load, then copper loss at fraction of load is equal to X square into PCU, and for the maximum efficiency, X square into PCU is equal to iron loss. Now solving it for fraction of load X, we have equation like this: root over iron loss divided by full load copper loss. Iron loss is 1 kilowatt and full load copper loss is 2 kilowatt. Therefore 1 by 2 or 1 by root 2 gives 0.707. We know that kVA for maximum efficiency is equal to load fraction multiplied by kVA rating of transformer, which is equal to X is equal to 0.707 and rating of transformer is 100, which gives us 70.7 kVA. Therefore, the correct answer is option C. Ninth question. A transformer is working at its full load and its efficiency is also maximum. The iron loss is 1000 watts. Then its copper loss at half of full load will be option A 500 watt, option B 400 watt, option C 300 watt, and option D 250 watt. Now, for maximum efficiency, we know that copper losses must be equal to iron losses. Here, iron losses are 1000 watt. Therefore, copper losses are also equal to 1000 watt. Now we know that copper loss is directly proportional to square of load. Now let us consider X is the fraction of load. Then copper loss at fraction of load is equal to square of the load fraction multiplied by copper loss at full load. Here value of X is 1 by 2 given in the question. Therefore, copper loss at half load is equal to 1 by 2 whole square multiplied by copper loss at full load, which is equal to 1000 watt. Therefore, 1000 divided by 4 gives us 250 watt. Therefore, the correct answer is option D. Copper loss at half load will be 250 watt. 10th question. Hysteresis losses are present in the core of an iron core coil when option A, the current is unsymmetrical alternating only, option B, the current in the coil is sinusoidal only, option C, the current in the coil is alternating only, and option D, the current in the coil is DC only. The question asks, hysteresis losses are present in the core of an iron core coil when what type of current flows? Now first understand the concept. Hysteresis loss occurs because the magnetic field inside the iron core keeps changing direction. This continuous magnetization and demagnetization happens only when the current is alternating. If DC current is applied, the magnetic field becomes constant after some time, so hysteresis loss does not continue. Also, the current does not have to be perfectly sinusoidal. Any alternating current can produce hysteresis loss. Therefore, the correct answer is option C. The current in the coil is alternating only. Now, important concept to remember: alternating flux causes hysteresis loss. Constant DC flux does not produce continuous hysteresis loss.